Hello, Chem 110. Let's go ahead and look at practice exam 1A. Our first question is asking which quantum number is needed to define a subshell. So let's go ahead and think about what each quantum number will define. So when we only know N, we know what shell our electron is in. When we also know L, then we know the subshell. If we additionally know M sub L, we know what orbital our electron is in. And if we know all four, including M sub S, we will now be describing a specific electron. And so to properly describe a subshell, we need to know both N and L. So we need everything up to that point. And so the answer here is B. Okay, for number 2, we're meant to calculate the volume of a gas given its mass and its density. And so we know density is mass over volume because we love density so much that maybe we hugged it a little too hard and split that heart in half. And see that M over V. And so we can use this relationship to solve for volume, but in order to do that we need to make sure that the units of mass match here for our calculation. And right now they do not. But we do know that micro kind of can be replaced with 10 to the minus 6th. And so what we can go ahead and do is say that this is 78.5 times 10 to the minus 6th grams. Okay, so then we can take that and say 78.5 times 10 to the minus 6 grams. So starting with what I'm given, and then I can use the density as a sort of conversion factor. So I need to put grams on the bottom. And what I see from that density that I'm given is that in 1 milliliter there will be 1.225 times 10 to the minus 3 grams. And after I go ahead and punch this in my calculator and solve, I can see that I will have 6.41 times 10 to the minus 2 mils, corresponding to answer choice C. And this kind of makes sense because a microgram, that's a really small amount. And so it shouldn't occupy very much volume. Okay. In number 3, we want us to figure out which photon has the highest energy, given some different wavelengths. And we know we can relate energy to wavelength through the equation E equals hc over lambda. And so the energy and wavelength are inversely proportional. So what that means is if I want to increase energy, I need to decrease wavelength. And so then the one with the shortest wavelength will have the highest energy, and that would correspond to photon A. And the constants H and C are written on the data sheet, so you don't need to memorize those or anything. Okay. In number 4, they're asking us to put some ions in order of increasing Z effective. Okay. So what I've done here is gone ahead and looked for their atomic numbers. Just look for the number on the periodic table for each one, because this number tells me how many protons each of the element has in the nucleus. And with effective nuclear charge, we're interested in that nucleus. And then all of these ions, if you look at the electron configuration, they all have the same one. They all have that krypton core electron configuration, meaning that we could consider these isoelectronic. So iso generally means same, so it's saying same electrons. So if we have the same electrons, but different protons, we can think about kind of how much of a pull the nucleus could have, depending on the charge in the center. And so in the case of the strontium, we have 38 protons pulling on 36 electrons. Whereas in the case of As3-, we only have 33 protons pulling on those 36 electrons. And so since there are more protons at the center pulling on the electrons, the strontium 2+ will have the highest Z effective. Br- in the middle, and As3- will have the lowest Z effective. And so in terms of size, that would mean this is the smallest of the three, and this is going to be the largest. So the answer here is C. In question 5, they want us to figure out which system has the lowest potential energy. And so we know that when we have charged particles, we can use Coulomb's law to rate the electrostatic potential energy. So I have Coulomb's law written here, where we have the charge of the particles multiplied together, divided by the distance. And so for this first interaction, we can see we have +2 for one of our charges, times +1 for the other charges, or other charge, divided by 2d. They go ahead and tell us they're twice as far apart as the middle one. And so when we solve that, we're just going to get +1 as our relative potential energy. And then if we look at our second particle, or second set of particles, we have a +1 charge, a -1 charge, divided by a distance of 1. So the potential energy here would be -1. And then for our last one here, we have a particle that is +2, -2, divided by 3d. So that would end up being -4/3, which is like -1 1/3. Okay, so we figured out their relative potential energies. And so we just want to pick the one that's lowest, so the most negative. And that is going to be C. And so that would be the most stable interaction, also the most favorable. Question 6 asks us to predict the charge that a group 2 element would have when it forms an ion. So our group 2 elements are our alkaline earth metals. They're things like magnesium and calcium. And they have a general kind of generic electron configuration where they have some core, some s, and then 2 s electrons. And so to reach a noble gas configuration, they happily give up their s electrons and become +2. Here in number 7, we really have to write out electron configurations. So they're asking us about complete octet for a bunch of different metals, or 3 different metals. And they have charges on them. They all have +2 charge, which means that we're going to have to remove some electrons. But I always like to start by writing out my neutral electron configurations first. And so for iron, the neutral electron configuration we have 2 s electrons and 6 d electrons. And then to make it iron 2+, now I need to remove 2 electrons. And I'm going to remove them from the shell that is furthest out. So the shell with the bigger N value. And so even though the 4s is slightly lower energy, that's where we're going to remove the electrons from. And that's the case for any of our transition metals. And so next for lead, its electron configuration, it's pretty big. It ends up having a xenon core, a full S subshell, full D subshell, and then 2 6p electrons. So to make it +2, we want to remove from a subshell that has the biggest N value, so that's going to be 6. And then if we're looking at 2 possible subshells with the same principal quantum number, we take it from the higher energy subshell. So we're going to remove 6p electrons. So 1, 2. Okay. And then we have barium. Has a xenon core. And then it just has those 2 s electrons. And so, if we need to make it +2, now we're going to erase those 2 electrons. And so that means barium is left just with its xenon core when it has a +2 charge. Just like we talked on the previous question when we were looking at our group 2 metals. And so barium here is the answer because it's reached a noble gas configuration, which means that its valence shell would be full, or it would have a complete octet. Here in number 8, we have a graph where we're looking at energy and distance. And so this distance is the distance here in Coulomb's law, so it's how far apart 2 particles are, and this energy is the same energy there. And so when we're way here on the right side of the graph, it means our particles are really far apart. And when we're on the left side of the graph, it means they're pretty close together. And so they want us to predict or pick which ones correspond to an attractive interaction. And so we know that when particles are attracted to each other, the energy is negative. And so we can see 0 here in the middle of our graph. And so when the curves are below 0, or negative, that means we have an attractive interaction. And those would be curves 3 and 4. Making answer choice B the correct. here we have, different subatomic compositions, and they want us to figure out which atoms are isotopes of each other. So when we're looking at isotopes, what we're going to have is the same number of protons, but different number of neutrons. And then we don't have to consider the electrons at all. And so the only ones that have the same number of protons as each other are 3 and 4. And then we can see they have different neutrons. So the correct answer here is C. Okay, number 2, we have a plot looking at what wavelengths of light are absorbed by two molecules, A and B, and we're supposed to pick which is more effective at absorbing low frequency light. And so we want to be able to relate frequency to wavelength, because wavelength is what's actually given to us on our plot. And so we can keep in mind that we have this equation relating those together, where the speed of light is equal to wavelength times frequency. And so these are inversely related, which means if one goes up, the other goes down. So if we want the lowest frequency light, we want the longest wavelength of light. So over here on the right on our graph is where we have our low frequency. And then we can see here that molecule B is what's absorbing at that position. So the answer here is B. In number 11, they want us to rank these types of light in terms of increasing energy. And so I'm going to start by just putting visible in the middle. And then we know that ultraviolet light is high energy because it's kind of dangerous. I actually just bought a UV sterilizing wand. So it kills stuff on because it's high energy. And so I'm going to put that up above visible. And then infrared is our longer wavelength, lower energy. So the answer here is D. Okay. For number 12, they want us to figure out which electron configuration is a violation of Hund's rule. Hund's rule is the share before you pair rule, and it's also the match your spins rule. And so what that means is if we have unpaired electrons, they either need to all be pointing up or all be pointing down. Doesn't matter between those two, they just all have to match. Okay. So, in answer choice A, this is an excited state because of the 3s electron. Right, we can see that an electron that would normally be in the 2p was excited up to the 3s. And that's in violation more of Aufbau's principle. So Aufbau's principle is the idea that you start from low and move higher when you're filling out electrons. So then answer choice B looks like that's the ground state of our element. Answer choice C seems fine. Also looks like a ground state. And then we can see in answer choice D, they did not share before they paired. And then if we do look at answer choice E, this is a violation of Pauli's principle, and this would be impossible. It's not an excited state, it's an impossible state. And so the correct answer is D. Here in number 13, we're picking out which is an allowed set of quantum numbers. And so here I've just written out the rules for what values different quantum numbers can have. So n has to be greater than 0, L has to be less than n, and then it can go down to 0, and then m sub L is on the range from L to negative L, and then m sub S has to be plus or minus 1/2. And so, truthfully, I always just look first at the m sub S and quickly cross out any that have a spin that is not plus or minus 1/2. Usually that's kind of the most obvious to pick out. And so then, if we look at A, we have n greater than 0, L is less than n, m sub L is equal to negative L, which is fine, and m sub S is plus 1/2. So A seems like a good choice. But let's go ahead and look at the other ones, make sure there's something wrong with each of those. So in B, n is greater than 0, but then we can see that we have L equal to n, and that is not possible. And then it looks like we have the same problem here in C. We have n greater than 0, but then L is equal to n. So for E, n looks good, L looks good. Our problem is m sub L, because the only possible m sub L value here would be between negative 0 and 0. So m sub L would have to just go ahead and be 0. Can't be plus 1. So we've confirmed that the correct answer is indeed A. So here we have some pretty pictures of some orbitals, and they want us to figure out which orbital could be associated with the given quantum numbers. And when we're looking at orbital shape, we're looking at the L quantum number. So n tells us about size, L tells us about shape, m sub L tells us about orientation in 3D space, and m sub S tells us about spin. And so if L is equal to 0, that means we have an S orbital, which will have a spherical shape. If L is equal to 1, it means we have a P orbital, which has that dumbbell shape. If L equals 2, we have a D orbital, which can either take the clover form or the donut around a dumbbell form. And so, since L is equal to 2, we want to look for the orbitals that match this. And that is going to be 2 and 3. Making the correct answer here E. Okay, number 15, we're looking at electron configuration, so it does help to have the periodic table handy for sure. And we can see that neutral phosphorus does indeed have a neon core, has 2 s electrons, and it does have 3 p electrons. So A looks good. So that's not going to be our choice. For B, as written actually, we have the configuration for neutral tin. And what we have is actually tin 2+, and so we need to have lost 2 electrons. And those electrons that we would lose would be the 5 p electron. Okay. And so B is not the correct configuration, so that is our answer. Then if you write out the configurations for these other species, you would see that they also have the correct electron configuration. And so just keep in mind when you're writing the electron configuration for ions, I really do think it helps to write out the neutral form first and then go through and either add or remove electrons. Okay. Here in question 16, we're looking at a system where heat and work are being exchanged. They go ahead and tell us that 5 kcals, or kilocalories, of heat are flowing into the system. So it's going to be an arrow pointing in. It's entering. I mean endothermic process with a positive 5 kcal. And then they tell us that the delta E overall is equal to negative 7.5 kcal. We remember that delta E is just equal to heat plus work. So this negative 7.5 kcals can be equal to a positive 5 kcals heat plus the work. And so then we can solve for work by just subtracting over the 5, and we can see that the work is negative 12.5 kcals. And so we would say that the system is doing 12.5 kilocalories of work on the surroundings. And that is answer choice A. Here in number 17, they want us to figure out what the correct ground state orbital diagram is for cobalt-3+. So I'm going to start by drawing the electron configuration for neutral cobalt. We have an argon core, 4s electrons, and then we have 7d electrons. So then to make this 3+, we need to get rid of 3 electrons. And so we're going to remove electrons first from the orbital that is furthest away. And that is going to be the 4s. So we're going to get rid of both of these electrons. And then we're going to get rid of one more electron. So we're going to take one of the paired electrons from the 3D. And so that is now our configuration for cobalt-3+, which corresponds to answer choice B. In number 18, we're figuring out which elements would have the most endothermic electron affinity. So it's going to be the most positive value for the electron affinity, which is going to mean least favorable. So basically we're asking which of these elements is less likely to gain an electron. And so our trend for electron affinity shows that it increases as you go down and to the left on the periodic table. And here we're just actually looking at one row of the periodic table, so we're just going to look to see which is furthest to the left. And that, oh, that's a tempting way to think about it, but we have one species here that really doesn't want to gain an electron or change its electrons at all. Doesn't want to gain an electron, doesn't want to lose an electron. And that element is neon. Neon is a noble gas. It has its full octet. It's hard to mess with those core electrons or add on anymore. Okay, so this would have the most endothermic electron affinity. Here in number 19, we're looking at some ionization energies. So ionization energies are the amount of energy we have to put in to remove an electron. And so here, we remove 1 electron, 2 electron, 3 electron. And then when we go to remove that 4th electron, there's a huge spike. It's a big jump in how much energy it takes. And so that tells me that this element is content to have lost 3 electrons. But then once we remove our 4th electron, we've gone in and removed a core electron. And that's why it takes so much energy. And so that tells me I had 3 electrons to give up, so I must be in group 3. Okay.